Today, I'm inviting you to join me on an epic journey into the very heart of technology. We are going to peel back the layers of the digital brain, the central processing unit, or CPU, to uncover the mind-blowing secrets of its birth, its evolution, and the incredible precision required to make the modern world function. Are you ready to see the world through a microscope and realize that the impossible is happening inside your pocket every second? To understand where we are going, we must first look at where the spark began. The history of the CPU is not just a timeline of gadgets. It is a story of human ambition shrinking the world. Our journey starts in 1971. We find the genesis moment of the Silicon Age, the Intel 4004. Before this, computers were massive, room-filling monstrosities made of discrete components wired together like a messy web of spaghetti. The 4004 changed everything by shrinking those functions onto a single chip. It was a turning point that shifted the trajectory of human history. Think of it like the transition from the horse and buggy to the jet engine. This breakthrough led directly to the Intel 8086, a processor that might sound like a relic today. But it was the very soul of the first IBM personal computer in 1981. That was the moment the personal computer wasn't just a hobbyist's dream. It became a tool for the masses. It was the first time an individual could own the power of computation, a power previously reserved for governments and giant corporations. We moved from a world where computers were out there to a world where they were on our desks. As we moved into the 1980s and 90s, the race for speed became the defining narrative of the tech industry. This was the era of the 80,286 and the 80386, chips that allowed us to do more than one thing at a time. Do you remember the first time you could listen to music on a computer while typing a document? That was multitasking, and it was revolutionary. Intel pushed the envelope, making chips faster and more affordable, which allowed IBM to flood the market with PCs. Then came the 1990s, the era of the Pentium. The word became synonymous with speed. Suddenly, computers weren't just for spreadsheets. They were for multimedia, 3D gaming, and the early screeching days of the internet. During this time, IBM wasn't just sitting back. They were developing the PowerPC architecture, trying to challenge Intel's crown. It was a clash of titans that forced innovation to happen at breakneck speeds. This competition is why, in just one decade, computers went from glowing green text on a black screen to full-color video and global connectivity. As the calendar flipped to the 2000s, the industry hit a wall literally. We couldn't just keep making chips faster because they were getting too hot. If we had kept going at that rate, a CPU would eventually become as hot as the surface of the sun. So the engineers got smart. Instead of one super-fast brain, they started building multi-core architectures. It is like moving from a single genius working a desk to a team of experts collaborating in an office. This shift focused on efficiency and power consumption, which is exactly why your smartphone can last all day on a single charge while being more powerful than a 90s supercomputer. During this time, the landscape shifted. IBM moved away from making your home PC and focused on the big iron, the massive servers and supercomputers that run the world's banks, research labs, and weather models. The Intel Inside stickers were everywhere, but the real magic was happening in how these chips learned to talk to each other across different cores, paving the way for the AI revolution we see today. Now let's get into the how. This is where the story turns into modern-day alchemy. The journey of a CPU begins with quartz sand, the most ordinary thing you can imagine. But to make a chip, that sand must be purified to an insane degree. We're talking about 99's purity, 99.9999999% pure silicon. If you had a pile of sand the size of a mountain, you couldn't have even a single grain of dust in it. This sand is melted at extreme temperatures and grown into a massive, heavy cylindrical ingot. It looks like a giant, shiny silver rolling pin. This ingot is then sliced into wafers, discs, thinner than a credit card, and polished to a mirror finish. This silicon wafer is the canvas upon which the most complex painting in human history will be created. It's a poetic thought, isn't it? That the silicon in our high-tech devices is just a highly organized, hyper-purified version of the Earth beneath our feet. Once we have our wafer, we need to draw the circuits. But you can't use a pen or a traditional printer. The features are too small for physical tools. Instead, we use light. This is called lithography. The wafer is coated with a light-sensitive chemical called photoresist. Then, using a machine that costs more than a fleet of private jets, we shine ultraviolet light through a mask, essentially a stencil of the chip's design. But here's the kicker. Modern chips use extreme ultraviolet EUV lithography. The wavelength of this light is so short it can print features just a few nanometers wide. To give you a real-life connection, a human hair is about 80,000 to 100,000 nanometers wide. We are printing billions of components in a space smaller than a speck of dust. This process is repeated dozens of times, layer upon layer, creating a 3D skyscraper of circuitry on a microscopic scale. Printing the pattern is just the beginning. After the light does its work, we use chemical and plasma etching to carve away the unprotected material, leaving behind the intricate channels of the circuit. But a circuit needs to be more than just a path. It needs to be a switch. This is where doping comes in. We bombard the silicon with ions elements like boron or phosphorus to change its electrical properties. This is like turning some parts of the silicon into conductors and others into insulators. We then use heat treatment to settle everything into place. These areas become the regions of the transistor, the actual gates that flip between 0 and 1, the yes and no that form the language of all digital logic. It's a delicate dance of chemistry and physics happening at the atomic level, ensuring that every single one of those billions of transistors works perfectly. Even after the transistors are built, they are useless unless they can talk to each other. This requires wiring. Imagine trying to wire a skyscraper where every room needs to be connected to every other room, but the entire building is smaller than a grain of salt. We deposit ultra-thin layers of insulating materials and metals, usually copper, to create these connections. This isn't just one layer. It's a vertical maze that can go up to 100 layers deep. Each layer must align perfectly with the one below it. If a single wire is out of place by a few atoms, the entire chip is garbage. This precision is what allows the CPU to operate at speeds of billions of cycles per second. Electrons zip through these copper highways with almost zero resistance, carrying the data that makes your screen come to life. Because the process is so impossibly difficult, it isn't always perfect. A single microscopic speck of dust falling on a wafer during production can ruin a dozen chips. This is why factories, fabs, are the cleanest places on Earth, thousands of times cleaner than a hospital operating room. Throughout the process, the wafers are scanned by metrology tools that can see things smaller than a virus. Once the chips are finished, they are tested. Some come out perfect. These become the high-end i9 processors. Some have minor defects in certain areas, so the engineers turn off those sections and sell them as i7 or i5 processors. This is called binning. It has a fascinating look at the economics of technology. Even the lower end chips are actually masterpieces of engineering that just didn't quite reach the perfect tier. Once the wafer is filled with working chips, we use high-precision lasers to slice them into individual squares called dies. But you can't just plug a raw piece of silicon into a computer. It's too fragile. It needs a suit of armor. Each chip is mounted onto a substrate and sealed with a heat spreader, that silver square you see when you look at a CPU. This helps pull the heat away from the silicon so it doesn't melt itself. Every single unit then undergoes a burn-in test. They are pushed to their limits under extreme heat and stress to make sure they won't fail in your laptop 3 years from now. Only the survivors, the ones that prove their reliability, are boxed up and shipped across the globe. This entire industry rests on the shoulders of just a few companies. You know, Intel, they are the pioneers, the ones who design and build their own chips. But there's another name you must know. TSMC, Taiwan Semiconductor Manufacturing Company. They are the world's foundry. They don't usually design their own chips. Instead, they are the master blacksmiths who build the chips for Apple, Nvidia, and AMD. And behind them all is ASML, a company in the Netherlands that is the only company in the world capable of making the EUV lithography machines required for modern chips. If any one of these three companies stopped working tomorrow, modern civilization would grind to a halt. The sheer concentration of high-tech knowledge in these few entities is one of the most significant geopolitical factors of our time. We often think of CPUs as just computer stuff, but they are the heartbeat of everything. Your car likely has dozens, if not hundreds, of microchips controlling the engine, the brakes, and the entertainment system. In hospitals, they power the MRI machines that save lives. In space, they hardened against radiation to guide rovers across the Martian surface. We are currently in a race to make these chips even smaller and more energy efficient. Why? Because the next frontier is artificial intelligence. AI requires massive amounts of data processing, and our current chips are being pushed to their absolute limits. The research happening right now in silicon photonics and quantum computing is aimed at one goal: keeping the brain growing faster than the problems we need it to solve. But the journey doesn't end at the chip factory. Those CPUs travel to massive assembly plants where the final devices are born. Here, robots work with human-like precision to solder the CPU onto a motherboard. They integrate the high-speed RAM, the storage drives, the cooling fans, and the vibrant screens. Each laptop is a symphony of thousands of parts, all working in harmony with the CPU as the conductor. Every connection is inspected by high-speed cameras, and every finished device is booted up for the first time in a quality control room to ensure that the journey from a grain of sand to a functional tool is complete. Finally, we have to look at the cost, not just the price tag, but the cost to our planet. Manufacturing chips requires immense amounts of water and energy. The good news? The industry is waking up. Giants like Intel and TSMC are moving toward 100% renewable energy, using massive solar farms to power their fabs. They are recycling water and finding ways to make chips that do more work with less electricity. As we move forward, the perfect chip won't just be the fastest one. It will be the most sustainable one. The future of technology isn't just about power, it's about balance. As I look at the complexity of a CPU, I realize a profound lesson. Small things matter. The entire digital revolution, the internet, social media, space exploration is built on things so small we cannot see them. The precision of a nanometer determines the success of a trillion-dollar company. In our daily lives, we often overlook the nanometers of our character, the small habits, the tiny gestures of kindness, the 5 minutes of extra effort. Just as a single speck of dust can ruin a $100,000 wafer, a single moment of neglect can stall our personal growth. But conversely, when we layer our small, positive efforts consistently, just like the 80 layers of a CPU, we build something mighty. My advice to you is this: don't be intimidated by big goals. Break your life down into nanometers. Master the small steps. Stay pure in your intentions. And you will eventually build a life that is as powerful and impactful as the chips we discussed today. Thank you so much for joining me on this deep dive today. Wishing you all the very best of health and happiness. And if you found this journey as fascinating as I did, please consider hitting that subscribe button and ringing the bell so you don't miss our next adventure into the heart of technology.